Welcome to the problem walkthrough for LeetCode number 60, Permutation Sequence. In this problem, we'll explore how to efficiently determine the KTH permutation sequence of numbers from 1 to n. By the end of this session, you'll understand the key concepts and approaches needed to tackle this challenge. Let's get started. The problem permutation sequence asks us to find the KTH permutation of the numbers from 1 to n, where the permutations are arranged in lexicographical or dictionary order. The task is to return this specific permutation as a string. For example, if n is 3, the set of numbers we are working with is 1, 2, 3, and k represents the position of the desired permutation when all permutations are listed in sorted order. The constraints for this problem are that n can range from 1 to 9, and k is a valid permutation index, meaning it falls between 1 and n factorial. The output is a single string that represents the KTH permutation in this sorted order. In the first example, we are given n equals 3 and k equals 3. The goal is to find the third permutation of the set, 1, 2, 3, in lexicographical order. When we generate all possible permutations of 1, 2, 3, we get the following sequence: 123, 132, 213, 231, 312, and 321. The third permutation in this list is 213, which is the output for this input. This demonstrates how the problem requires us to determine the KTH permutation based on the sorted order of all possible permutations. In the second example, n is 4 and k is 9. This means we are working with the set 1, 2, 3, 4, and we need to find the ninth permutation in lexicographical order. When we list all permutations of this set, the sequence begins with 1234, 1243, 1324, and so on, until the ninth permutation, which is 2314. This solution highlights the scalability of the problem as n increases, and the importance of an efficient approach to avoid generating all permutations explicitly. In the third example, n is 2 and k is 2. The set of numbers is 1, 2, and the task is to find the second permutation in lexicographical order. Listing all permutations, we have 12 and 21. The second permutation is 21 foot, which is the output. This example demonstrates a smaller case, where the problem is straightforward but still follows the same logic of identifying the KTH permutation from a sorted list. The constraints also ensure that we consider edge cases, such as when n is at its smallest or largest possible value. Some key observations about this problem help us approach it efficiently. First, the total number of permutations for a set of size n is n factorial, which means the solution involves factorial calculations. Second, because the permutations are sorted lexicographically, we can determine the KTH permutation directly by leveraging the structure of factorial blocks. Instead of generating all permutations, we can skip unnecessary computations by calculating which block the KTH permutation falls into, and then sequentially removing elements from the candidate set. This approach significantly reduces computational overhead and allows us to solve the problem efficiently, even for larger values of n. To solve the permutation sequence problem, one possible approach is the brute force method, where we generate all permutations of the numbers from 1 to n. The idea here is to first compute every possible arrangement of these numbers, then sort them in lexicographical order, and finally return the KTH permutation from this sorted list. We can use a backtracking algorithm to systematically build all permutations recursively. However, the major drawback of this approach is its inefficiency. The time complexity is n*n, because we need to generate n permutations and then sort them, which adds further computational overhead. For larger values of n, such as n greater than 9, this method becomes impractical due to the sheer number of permutations involved. This is why, despite being conceptually straightforward, this approach is not suitable for solving the problem efficiently. A much more efficient strategy is the optimized mathematical approach, which avoids generating all permutations entirely. The key insight here is to use the properties of factorials to directly calculate the KTH permutation. Here's how it works. Permutations of n elements can be grouped into n1. subsets based on their first digit. For example, with n equal to 3, we have 3 groups, those starting with 1, those with 2, and those with 3. The position of k within these groups tells us which group, and therefore which digit, should come first. Once the first digit is determined, the problem reduces to finding the kth permutation of the remaining digits, with k adjusted to reflect its position within the smaller group. To implement this, we precompute factorials for quick access and maintain a list of available digits. Iteratively, we determine each digit by dividing k by the factorial of the remaining digits and then selecting the corresponding digit from our list. After selecting, we remove the digit and update k. This process repeats until all digits are resolved, resulting in the kth permutation. The time complexity of this approach is n squared, primarily due to the repeated removal of elements from the list, which takes n at each step. This method is efficient, avoids unnecessary computation, and directly calculates the desired result. Another option we could consider is using Heap's algorithm, which generates permutations directly in lexicographical order. With this method, we could stop once the kth permutation is generated. While this approach avoids the need to sort permutations afterward, its complexity is still k*n. For large values of k, this remains suboptimal compared to the mathematical approach. Ultimately, the optimized mathematical approach was chosen as the best strategy. By leveraging factorials, we were able to partition permutations into manageable groups and precisely determine each digit without generating extraneous results. This method strikes the ideal balance between simplicity, clarity, and performance, making it significantly more efficient than brute force or alternative solutions. To solve the problem of finding the kth permutation sequence of the numbers 1 to n in lexicographic order, we can start by examining a brute force approach. The first step is to generate all possible permutations of the numbers from 1 to n. This can be achieved by using a backtracking method, which systematically explores all potential orders of the numbers by adding one number at a time to a current sequence. For example, when n equals 3, the generated permutations would include sequences like 1, 2, 3, 1, 3, 2, and 2, 1, 3, among others. Once the permutations are generated, they are stored in a list. This ensures that we capture all valid permutations of the desired length, n. Finally, the list of permutations is sorted in lexicographic order, which is essentially dictionary order. Sorting allows us to directly access the kth permutation using its index, making it easier to retrieve the desired result. Once all permutations are sorted lexicographically, the next step is to fetch the kth permutation. Since lists in most programming languages are zero-indexed, the kth permutation corresponds to the k1 index in the sorted list. We can then return this sequence as the final result. A key insight here is that sorting the permutations ensures they follow dictionary order, which simplifies the retrieval of the kth sequence. However, this brute force approach comes with significant computational costs. Generating all permutations requires n time, and sorting them adds an additional n log n complexity. This makes the approach feasible only for small values of n, typically n less than or equal to 7. The use of backtracking is essential here, as it systematically explores all possible combinations by tracking choices and undoing them when necessary. In terms of data structures, we use a list to store the permutations, a temporary array to build each permutation step by step, and a set to keep track of which numbers have already been used in the current sequence to avoid duplicates. Let's walk through an example to see how this approach works. Suppose the input is n equals 3 and k equals 3. The first step is to generate all permutations. Starting with an empty sequence, we recursively add numbers that haven't been used yet. The first permutation generated is 1, 2, 3, followed by 1, 3, 2, and then 2, 1, 3, continuing until we've generated all 6 permutations for n equals 3. After the permutations are generated, they are sorted in lexicographic order. In this case, the permutations are already in order 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Since k equals 3, we retrieve the third permutation from this sorted list, which is 2, 1, 3. This demonstrates how the brute force method works step by step to find the kth permutation. In certain edge cases, this approach remains straightforward. For instance, if n equals 1, there is only one possible permutation, 1, regardless of the value of k. Similarly, if k equals 1, the result will always be the first permutation, which is 1, 2, n. On the other hand, if k equals n factorial, the result corresponds to the last permutation in lexicographic order. While this brute force approach is simple to understand, its limitations become clear for larger values of n due to the exponential growth in both time and space complexities. The approach requires n time to generate all permutations and additional space to store them. For values of n greater than 7, this method becomes impractical, and optimization is critical. One such optimization involves using mathematical properties, like factorials, to directly compute the kth permutation without generating all permutations. This optimized method is significantly more efficient and addresses the limitations of the brute force approach. This solution efficiently computes the kth permutation sequence without generating all permutations. Here's a breakdown of the approach. 1. Pre-computing factorials. We calculate factorials for numbers 1 to n and store them in a list. This helps us determine the size of permutations for each remaining digit as we build the sequence. 2. Building the numbers list. We create a list of strings representing the numbers from 1 to n. This list will be modified as we select digits for the kth permutation. 3. Zero-based index adjustment. Since permutations are typically indexed from 0 in programming, we adjust the given k by subtracting 1. 4. Iterative selection. Starting from the highest position, n, we determine which digit to pick for the current position using the formula id x equals k // factorials, I1. This index is used to extract the appropriate digit from the numbers list. After extracting the digit, we update k using k % equals factorials, I1, to prepare for the next iteration. 5. Building the result. The selected digits are added to the result list. After all iterations, the result list contains the kth permutation in order. 6. Final output. The result list is joined into a single string and returned as the output. This approach has a time complexity of n squared due to the repeated list operations, removals, but it avoids generating all permutations, making it much more efficient than a brute force solution. The space complexity is n for the factorials and numbers lists, as well as the result list. To solve the problem of finding the kth permutation sequence, we start by pre-computing the factorials for numbers from 1 to n. This is essential because factorials help us determine the number of permutations for each subset of numbers, allowing us to navigate through the sequence efficiently. Here, we initialize an array called factorials, where factorials, 0, is set to 1, and then iteratively calculate the factorials for all numbers up to n. After that, we construct a list of numbers from 1 to n, which represents the elements we can use to form the permutations. At this point, we also adjust the given k to a zero-based index by decrementing it, as it simplifies the calculations when working with arrays. Finally, we begin building the kth permutation iteratively using a string builder. For each position in the permutation, we determine the index of the current number by dividing k by the factorial of the remaining digits, and then append that number to the result while simultaneously removing it from the list of available numbers. After determining the index and appending the selected number to the result, we update k to reflect its position within the smaller subset of permutations. This is done by taking the remainder of k divided by the factorial of the remaining digits. By repeating this process for all positions, we effectively narrow down the sequence one step at a time, ultimately constructing the kth permutation. Once all numbers have been selected and appended, what remains in the string builder is the desired permutation sequence. The final step is to convert the string builder to a string and return it as the result. This approach ensures that the solution is both efficient and avoids generating all permutations, making it suitable for large values of n and k. To solve LeetCode problem number 60, permutation sequence, we need to determine the kth permutation of the numbers from 1 to n arranged in lexicographical order. The key here is that we accomplish this without generating all permutations explicitly, which would be computationally expensive. For example, if n equals 3 and k equals 3, we start by precomputing the factorials of numbers from 1 to n. These factorials represent the number of permutations that can begin with any specific number. For instance, factorial 2 equals 2, indicating that 2 permutations start with each number at the first position when n is 3. Next, we create a list of numbers available for permutation, 1, 2, 3. This list will help us track which numbers are still available for constructing the kth sequence as we go through the process iteratively. Now, since k is given as 1-based, we adjust it to a 0-based index by subtracting 1, making k equal to 2. This adjustment aligns with the indexing used in our calculations. To determine the kth permutation, we iterate from n down to 1, selecting one number at each step based on the factorial values. In the first iteration, with n equal to 3, we calculate the index of the number to select as k divided by factorial 2. This gives us an index of 1, corresponding to the number 2 in our list. We append 2 to the result, remove it from the numbers list, and update k to the remainder of k divided by factorial 2, which is 0. Now, our numbers list contains 1, 3, the result list is 2, and k has been updated to 0. Continuing with the iterative process, in the second iteration, n is now 2. We calculate the index as k divided by factorial 1, which gives 0. This tells us to select the first number in the list, 1. We append 1 to the result, remove it from the numbers list, and update k. The numbers list now contains 3, the result list is 2, 1, and k remains 0 because the remainder of k divided by factorial 1 is also 0. In the final iteration, with n equal to 1, the index is again 0. We append the only remaining number, 3, to the result and remove it from the numbers list. At the end of this process, our numbers list is empty, and our result list contains 2, 1, 3. The iterative construction of the kth permutation is now complete. To generate the final output, we simply join the elements of the result list into a single string. In this case, joining 2, 1, 3 gives us the output 213. Now, let's look at another example where n equals 4 and k equals 9. First, we precompute the factorials of numbers from 1 to n, which results in 1, 1, 2, 6, 24. These values will guide us in determining the number of permutations for each step. Then, we create the list of numbers available for permutation, 1, 2, 3, 4. With these two components in place, we adjust k to 0-based indexing, so k becomes 8. This prepares us to iteratively construct the kth permutation. Starting the iterative process for n equal to 4, we calculate the index for the first number as k divided by factorial 3, which is 8 divided by 6, resulting in 1. This points to the second number in our list, 2. We append 2 to the result, remove it from the numbers list, and update k to the remainder of k divided by factorial 3, which is 2. The numbers list now contains 1, 3, 4, and the result list is 2. In the next iteration, with n equal to 3, we calculate the index as k divided by factorial 2, which is 2 divided by 2, yielding 1. This corresponds to the second number in our updated list, 3. We append 3 to the result, remove it from the numbers list, and update k to 0. The numbers list becomes 1, 4, and the result is now 2, 3. In the third iteration, with n equal to 2, the index is calculated as k divided by factorial 1, which is 0 divided by 1, resulting in 0. This means we select the first number in the list, 1. We append 1 to the result and remove it from the numbers list. The numbers list now contains 4, and the result is 2, 3, 1. Finally, in the fourth iteration, with n equal to 1, there's only one number left in the list, 4. We append 4 to the result and remove it from the list. The numbers list is now empty, and the result list is 2, 3, 1, 4. At this point, we have successfully constructed the KTH permutation for this input. For the last example, where n equals 2 and k equals 2, we follow the same process. First, we precompute the factorials, resulting in 1, 1, 2. Then, we create the numbers list, 1, 2. After converting k to a zero-based index, k becomes 1. Now, we start building the KTH permutation. In the first iteration, with n equal to 2, the index is calculated as k divided by factorial, 1, which is 1 divided by 1, giving 1. This corresponds to the second number in the list, 2. We append 2 to the result, remove it from the numbers list, and update k to the remainder of k divided by factorial, 1, which is 0. The numbers list is now 1, and the result list is 2. In the second and final iteration, with n equal to 1, there is only one number left in the list, 1. We append 1 to the result and remove it from the list. The numbers list is now empty, and the result list is 2, 1. Joining these elements gives us the output 21 foot. This concludes our solution walkthrough for this problem. To understand the time complexity of the algorithm, we need to examine each step in detail. First, we have the precomputing of factorials. This step involves calculating the factorial for integers from 1 to n using a single loop. Since each iteration takes constant time, the overall time complexity for this step is O, n. Next, we create the numbers list, which contains strings representing numbers from 1 to n. This requires iterating through a range of size n, so this step also takes O, n, time. The most computationally intensive part is building the KTH permutation. For each of the n elements, determining the index involves a constant time division operation. However, removing an element at a specific index from a Python list has a worst-case time complexity of O, n, because the remaining elements need to be shifted. Since this removal process is repeated n times as we construct the permutation, the total time complexity for this step is O, n squared. Together, these contribute to the overall time complexity of the algorithm. Once the result list is built, the final step is to join its elements into a single string. This operation involves concatenating n elements and runs in O, n, time. When we add up the time complexities of all the steps, the dominant term is O, n squared, which comes from the repeated removal operations in the permutation construction step. Therefore, the overall time complexity of the algorithm is O, n squared. Now, let's take a look at the space complexity. The algorithm uses a factorials array to store precomputed factorials for integers from 0 to n. This array takes O, n, space. The numbers list, which initially holds n strings representing single-digit numbers, also requires O, n, space. Additionally, the result list, which grows to size n as the KTH permutation is constructed, contributes another O, n, to the space complexity. Other variables, such as k, idx, and loop counters, occupy constant space. When we sum these contributions, the dominant term is O, n. Thus, the overall space complexity of the algorithm is O, n. If we compare this algorithm to the brute force method, the efficiency becomes very clear. A brute force approach would involve generating all permutations of the numbers 1 to n, sorting them, and then selecting the KTH permutation. Generating all permutations has a time complexity of O, n, and requires O, n, space to store them, making it significantly less efficient. In contrast, our algorithm avoids generating all permutations, which is why it performs so much better. Furthermore, the algorithm has consistent performance for any input. Regardless of the values of n and k, the sequence of operations remains the same. This means that the time and space complexities are O, n squared, and O, n, respectively, in the best, worst, and average cases. Finally, we can mathematically justify the O, n squared, time complexity. The repeated removal of elements from the numbers list is what dominates the runtime. For each iteration, the cost of removing an element is proportional to the size of the list, which decreases from n to 1. Summing these costs gives us n plus n1 plus n2 plus 1, which equals n asterisk n plus 1 slash 2. This simplifies to O, n squared, confirming the quadratic time complexity of the algorithm. When solving the permutation sequence problem, there are several common pitfalls to be aware of. First, zero-based indexing is a critical aspect that can often trip people up. Many permutation algorithms, especially those using factorial numbering, assume a zero-based system. Forgetting this can lead to off-by-one errors when trying to identify the KTH permutation. A simple fix is to subtract 1 from k when translating it to a zero-based index. Next, brute force approaches might seem tempting, but they are highly inefficient for large values of n due to the O(n) complexity. Instead, it's better to leverage mathematical properties, like factorial groups, to directly compute the desired permutation. Another frequent source of error is incorrect factorial calculations. Miscomputing values or failing to precompute them efficiently can lead to redundant operations or outright mistakes. Precomputing factorials iteratively or using a helper function can prevent this. Lastly, mismanaging mutable lists is another area where errors can creep in. Operations like removing elements while constructing the permutation can inadvertently cause index errors or other side effects. To avoid this, ensure that list modifications are performed carefully with proper bookkeeping in place. Handling edge cases is another critical aspect of solving this problem effectively. For instance, values like n equals 1 or k equals 1 are simple but can easily be overlooked, causing the algorithm to fail. Explicit checks or assertions for these scenarios can help ensure your solution is robust. From an interview perspective, understanding factorial-based grouping is key. Optimal solutions often rely on dividing permutations into groups of size n/n and iteratively narrowing down to the correct group. Be prepared to discuss the inefficiency of brute force approaches, which operate at O(n), and contrast that with optimized solutions that reduce the complexity to O(n squared). Testing edge cases like n equals 1, k equals 1, and k equals n demonstrates a thorough understanding of the problem. Additionally, it's important to clearly explain trade-offs, such as why brute force methods are impractical and how optimized methods improve performance. Lastly, always clarify constraints with the interviewer, like verifying whether k is guaranteed to be within the valid range of 1 to n, to avoid unnecessary assumptions. The permutation sequence problem has connections to several related problems. For example, Problem 31, next permutation, focuses on generating the next lexicographical permutation, while Problem 46 generates all possible permutations of a given array. Problem 47 is an extension of this, generating all unique permutations while accounting for duplicates. And of course, Problem 60 is directly concerned with finding the KTH permutation, making it the core focus here. When it comes to alternative approaches, recursive backtracking is a common method, where permutations are generated recursively until the desired one is reached. This method is simpler to implement but becomes inefficient for large n due to its O(n) complexity. A more efficient approach is iterative factorial grouping, which uses factorial-based indexing to build the permutation step by step. This reduces complexity to O(n squared, but requires careful management of indices and mutable lists. Another option is Heap's algorithm, which systematically generates all permutations efficiently. However, since it's designed for generating all permutations rather than directly finding a specific one, it's not the most optimal choice for this problem. Great work completing this walkthrough. Today, we covered how to find the KTH permutation efficiently and discussed both brute force and optimized approaches. Remember to practice similar problems to solidify your understanding. Thank you for watching, and don't forget to like, share, and subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, Please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!